So in strategic form, what we saw was there were three things to represent the tuple: the number of agents, the strategy set or the actions for each of these agents, and the utilities for each of the agents, utilities or payoffs. In the extensive form, what we saw was it's a more elegant way to represent dynamic games wherein agents keep coming to the system and interacting with the system. And there we have a number of agents, we have a separate action space for each of the agents, and then we have Z. What is Z? Does anybody remember? So Z is the space of outcomes, which is the terminal set of history. You drew a tree, and at the end, we had all the possible outcomes after everybody made every move, right? So those tuples together form this C, which are the terminal history. What is P?
Where the action is taken, the point.
So what P is a function that maps what and what?
Information set to actions.
From information set?
No. Action and strategy. That's
Yes,
the
yes.
player of it.
It maps to SZ to N. So it maps from every subhistory. Which of the player has to take an action? That's what we wanted to represent in P. Right? So it maps subhistory, that is any paths from the root node to any of the subsequent nodes, to which is the player who is going to take an action. Then I, what is I? Information set. And then we have the U. It is a bracket list. Then we had games with perfect and imperfect information. What is perfect and imperfect information?
You know about all the information of the above actions.
What was the definition of it? Yeah. So the information set was a single thing. And imperfect information is at any point of time, if you don't really know what was the previous action, then it's an imperfect. There will be at least one information set of at least one agent, which is not single. Right? In that case, it would be an imperfect information game. Then we saw that we had a different definition of what strategies are in an extensive form game, right? And they were different from actions, right? They are different from the corresponding actions that we have over here. Then we had ways to convert the normal form or strategic form is the same. So we had ways in which we can represent extensive form in a normal form. Okay? And that's it. That's what we saw. And we also had one thing that you could represent multiple extensive form games using a single strategic form. Those were the things that we saw in the previous days. So in this class, what we will see is we use these utilities or payoff vectors for each of these agents. So what is the deal with them? How do we get these utilities? How are utilities actually defined? Or what do we really need a definition? Isn't it obvious? Utilities are something that you value, some value that you associate. But how do we know what is your utility? How do we elicit it from the agents? And then this leads us to we'll also understand certain basic assumptions that we make in game theory regarding the utilities. We also have this notion of common knowledge that we will try to see what is common knowledge in this game. And then we'll see what is rationality. What does it mean that what does it mean when we say agents are rational? Right? All of this relates to rationality, heavily relates to utilities. And then we'll see what is this assumption called intelligence. And these two are related, intelligence and common knowledge. Rationalities and utilities are related. And then we'll see what is best response strategies. So in today's class, what essentially we are going to establish is the basic assumptions that we have in game theory. And the basic assumptions are essentially these. Now, why do we need such an assumption? We need to determine what an outcome of the game is. So at what helps us determine what an outcome of a game or equilibrium of a game is are these assumptions. So we have certain way of defining what utilities are, which tells us what is rationality, what is the assumption of rationality. And then we assume that agents are intelligent, which tells us what is common knowledge. And based on these, we will try to determine what is best response strategies for each agent. Now, based on that, in the next few classes, we'll see how do we determine outcomes of games, equilibriums of games. Right? So that's what we are going to see today. Without there are new pieces. And this is the reading material for today. I'm not sure if the first book is available. It's quite a classic book and it's a very good read. You guys should take time to read it. Yeah, Narhari's book. So I have really used borrowed content from chapter 2 and partially from chapter 8. This 8 is the utility theory chapter. 2 is, I suppose, the key notions, what is common knowledge, etc. And these has got very, very, very nice things. So you should definitely read this. So in part 1, 6, 7, 8, 9, in heavily 9. This is what you should refer to for today. Okay. So this, so for people who are like who were not there in the previous class, so this is a strategic form representation of this game called Prisoner's Dilemma. In Prisoner's Dilemma, we have two agents, A and B, and each of these agents have two different actions or choices to make. That is either to confess or not confess. What this is essentially is that we have either two prisoners or two who have committed some crime and people know that they have committed, or it is two students, like I had explained, who were caught cheating. Now, what we have done is we have kept them in two separate rooms, so they are not able to communicate with each other. And now each of them is being asked to make a decision. Now, they are being asked to either confess that they have cheated or they have committed crime, or not confess. So these are the two options that they have available. And what are these values? So whenever both of them do not confess, then there is a deduction of marks from both of them, and that deduction is 2. Or in case of prisoners, it is the jail time that they get. So whenever both of them don't confess, there is a negative utility of 2, because we assume that deduction of 2 marks is exactly a deduction of -2 from their utilities, or imprisonment of 2 years is exactly a deduction of marks. If one of them confesses and the other does not confess, then the one who confesses is let off life with just a year time in prison, and the one who does not confess gets more pain. Then both of them confess, they share the utility, the negative utility, or 5 years of jail time. So this is how the matrix looks like. So essentially, the -2 or -10 here represent the reduction in marks or jail time. And that's what we have populated the matrix with. But what if A wants more jail time? Like, what if it's not really a negative utility for A to be in jail? For example, in many countries, the jails are better than staying outside homeless, right? So they probably want to stay in jail for longer. So now, what if A wants more jail time? Or what if, I don't know, A likes B, so A wants less jail time for it. Now, so are these values that we populated really representative of agents' preferences? Yeah, right. So we have to really understand. So just assuming that 2 years jail time is going to be a negative utility for them is not the right thing to do. We have to have so if I go ahead and analyze this matrix and try to get what is the best outcome, that may not really be the true scenario, because we are not even representing their preferences correctly. Right. So the first idea is in game theory to represent what their preferences are in a right order. Right. And is it possible to even represent everybody's preferences using numbers at all possible times? So all of these things is something that we will see. So the idea is that the prisoner's dilemma. So what do I mean by preferences? What is actually what am I trying to rank or order in this case? So the prisoner's dilemma game has 4 possible outcomes or strategies, or these are also called the strategy profiles. So these are O1, O2, O3, and O4. Now these all possible set of possible outcomes will have a corresponding utility attached, right? So these are the 4 possible outcomes. Now what I want to do is to know the preferences that each of these agents has over these 4 possible outcomes. So, the goal is to determine the utilities or numbers that represent the agent preferences. Now, this is a particular topic which has been researched quite a while before, and people have come up with these surrogate theories. But of late, this is sort of something that is sort of holding back game theory in some sense, because we don't really know how to extract utilities from it. So that's a bit of a thing that I wanted to mention before. Now, let's consider a game. Yes, is there a question or?
Yeah, ma'am, could you please repeat that last part? We haven't been able to extract utilities. Could you please explain that again? I missed it.
No, the thing is, we need to know what the preferences of agents are for all these outcomes. Right? In a real world, if I'm trying to model any real world scenario using game theory, I can model it only if I know what the agent utilities are, right? And to represent the agent utilities, I need to go and ask them what is their preferred. These are the 4 possible outcomes, and what is your preferences over these outcomes? This is something I need to be able to extract out of those agents. Then I model the game, and then I solve the game, right? So in game theory, there are a lot of ways on how to solve the game, and after the utilities are given, what is the best equilibrium and things like that. But how do you get the utilities is something that is not covered extensively, is what I'm trying to say.
Okay, got it. Thanks, ma'am.
Yes. So let's consider a generic game. There are 2 agents, each A has 3 actions, B has 2, and these are all the possible outcomes. Now, how do we get the preferences? We go and ask A, do you prefer O1 or O2? That's that's the only way that we can ask for preferences to A. But what if O1 is sky and O2 is apple? What would A say? Do you prefer sky or do you prefer apple? So it is something that it cannot compare, right? So A will say, I don't know. In that case, how do we actually we cannot really populate the matrix in that case? Or the other thing could be, A might say that I prefer O1 over O2. There is an outcome 1 that I prefer the other outcome, which is 2. And then it says that I prefer O2 over O3. And then it says that I prefer O3 over O1. So can you give me some utility numbers over these 3 that represent these preferences? You cannot. Why? Because there is so if let's say agent A prefers O1 over O2. So I put a utility of 100 for O1. Sorry. Utility of O1 is equal to 100. And since it prefers O1 over O2, I give less utility to O2, which is 50. What utility should I give to O2? Since since agent prefers O2 over O3, I can get I must give something less, right? I can get 0. But then that would contradict the last one, right? Because it prefers O3 over O. But if I give something more than 100, if I give 200, then this will be fine, but it will contradict this. So if agent has preferences like this, I'm not sure if you can come up with a real life scenario where the preferences will be cyclic or something like this. But if that is the case, then we cannot really come up with these utility numbers. So the idea is, if there are a set of outcomes O, and then player A's preferences must satisfy certain instincts for us to be able to come up with these utility numbers. And these axioms were given by von Neumann and Morgenstern. And there are 6 of them. But from the previous example, what we could see was there should be at least 2. One is called the completeness axiom, or that which means that they must be able to compare every pair of outcomes. That should be there. And the other axiom is transitivity. That means this should be true. If any agent prefers weakly prefers, so this notation, which is curly braces, that means it's preferences. It just means agent 1 prefers the outcome O1 over O2. And if it weakly prefers O2 over O3, then it should imply that O1 is preferred over O2. So this transitivity must be satisfied. So these are the 2 axioms that must be satisfied. Now, there are 2 ways in which we could come up with the we could denote the preferences. One is we could simply rank the outcomes. I don't really need to associate a number to it. I just need to know I prefer outcome 1 the most and some other outcome the least, and the order in between. So this is called ordinal ranking, ordinal preferences, wherein I don't really have a number to it, but I just rank it in some order. So let's say I prefer O1 over O2 over O3 and over O2. So this is one ordinal ranking. So I can have a number which represents this ordinal ranking. I really prefer outcome 1, then 3 to 1. This is the numbers that I have given. Maybe it could be monetary profit that I'm earning out of these outcomes. Let's say I have a different set of outcomes wherein I prefer all the 1, 2, 3 at 3 and 4 at 3. Both of these will have the same ordinal preferences, right? Is that clear? The numbers are very different, so there is a difference in which how I prefer each of these outcomes, but the ordinal ranking for both of these is the same. So the idea is that ordinal preferences only captures order, and it does not capture the intensity with which I prefer a certain outcome. This in turn, but what is the catch here? The catch is that to determine the outcome of the game, we don't only need the ordering, we also need the intensity. What is the final outcome that the game will have? For that, we'll need both the ranking and also the, or else we'll just, if we are given the cardinal utilities, we already know what the ordinal is. But cardinal utilities are required. Often in some games, we do not really need the cardinal utilities, but the idea is to come up with these cardinal utilities so that we have the maximum information possible to come up with the outcome of it. Now, how do we extract these utilities? I can ask these agents, what do you prefer, O1 over O2, etc., and I can come up with an ordinal ranking. But how do I come up with these numbers? It's something that has been given by the Neumann and Morgenstern, and that has to extract that they define this term called lotteries. This is what is used to come up with the numbers. So what we do in lotteries is the following thing. We ask the following questions. Do you prefer O1 over O2? Now, if it says yes, I'll just assign some number to O1 and I'll assign some less number to O2 because it prefers O1 over O2. Then what I ask is this lottery comparison. What I say is, there is this third outcome O3. Would you prefer the third outcome for certainty? So outcome 3 will happen with 100% probability. Do you prefer that? Or do you prefer an outcome where I give you O1 with probability half and O2 with probability half? Right. So there are 2 options that I'm giving. Do you completely prefer O3 with 100% guarantee, or O1 with half probability and O2 with half probability? Okay. Let's say if it says I prefer O3 for certainty, then what can we infer about the utility of O3 for agent 1?
First, then it is greater than O1 and O2.
Greater than O1 and O2 both? So O1 is, utility for O1 is 100. Utility for O2 is 0. And it prefers O3 with certainty over over O1 with half probability and O2 with half probability. So what can we say about the utility that one will get if outcome 3 happens.
Lesser than over than greater than over.
But what will be the exact value? I said half probability over. So the idea is that if O2, O1 happens with half probability, I get utility O1 with probability half and utility O2 with probability half. And this, so utility is greater than this. Sorry?
Greater than or equal to or
Greater. Okay. So there is a thing, if it strictly prefers over it, then there'll be a greater than equal to. If I just say just prefer, if I say strictly prefer, then there won't be an equal to. If I just say prefer, you can put
with expected utility.
yes. It's a utility if for a given lottery. Lottery is essentially this, a particular probability that are assigned to each of the possible outcomes.
And how we
Then that number will be just put those numbers. Right? So if if the utilities are both 100, then it will be half times 100 plus half times 100. So I'll be preferring O3 is more than 100.
following the same thought. If we like you said, if you prefer U1 F1 is 100, U2 go to 100, U3 or U1 or 3 is also 100. So I prefer all the same.
Yes, that is also an information. Hey, you prefer all the 3 at the same value is also fine. Right. So this is what we have. I prefer O3 by at least 50, equal to, if you will. Now, what I ask more is, do you prefer O3 for certain, or a lottery that gives you O1 with 3/4 probability and O2 with 1/4 probability? And let's say it answers, I prefer the lottery over the outcome only. So now what will be my range of utility?
So greater than equal to 75.
Greater than? Okay, I'm saying I prefer the lottery.
Certain or
Less than. Okay, let me just write it down. So I prefer 3/4 utility of 1 plus 1/4 times 0, which is, I prefer this more than utility of 4. And I know that I prefer it at least 4. So this value is
Please again continuation of the
50 is a continuation of the previous. I already know that utility is at least 50. But now I know that it is at most 75 because there is a lottery that I asked agent 1 and it prefers this particular lottery more.
focus on the same wording.
Yes, I did not say what it prefers. I just asked what it prefers. So it prefers the lottery more and not O3. Previously it preferred O3, now it prefers the lottery. So now I still don't know what the exact utility of O3 is. I'll keep asking, I'll keep defining such lotteries which help me narrow down the particular number for O3. Right? There'll be some combination of the lotteries that it will prefer O3 exactly at that. And that's also an assumption that we are making. But okay. So, and once we ask that, we know what O3 is. And likewise, we'll ask the utility, what the utility that it has for every possible outcomes for this particular game. That's how we come up with these utilities. And now there is also one more glitch that could happen. For example, what if A says, I'm indifferent to O1 and O2. Right? There are 2 outcomes and I equally like them. For example, it could be laptop, it could be Dell and HP. Right? I'm indifferent between Dell and HP. So I prefer the lottery which gives me del with probability 0.3, and this is something else. This is, let's say, Apple. OT is Apple. Apple with 70% probability. And I prefer the outcome. So this is so although I don't have any preference between del and HP, but there is a lottery wherein which gives me del with 30% probability, Apple with 30% probability. And there is another lottery which gives me HP with 30% probability and Apple with 70% probability. So these two lotteries are essentially the same. I'm just replacing the del over here with HP. Given that I'm indifferent to del and HP, what should my preference be between these two lotteries?
You should have indifferent as well.
Are you following? So I should also be indifferent to these lotteries as well. But what it says is I prefer this lottery over this. So now how do I assign numbers which gives me the same utility for both these, both del and HP, but different utilities? I really can't, right? Are you able to see? So again, such sort of issues will come up. So we need more axioms to pin down the fact that we are able to come up with some utility numbers, right? We already have two axioms. One is completeness and the other is transitivity. Now, to cater to such issues, we also need furthermore axioms.
But it does not have any to tell an how can we come up with that misalignment for this?
We can't. We can't. Let's be assumption. It is possible that this is somebody speaking online. Right. It's possible that they have certain preferences because I don't know, Dell provides some compatibility with Apple and it doesn't provide it with this. But in our current scenario, we can't really come up with anything.
That's not either he will tell or Apple.
No, this lottery is so either he will win one, but the probability with which he will get Dell is 30%.
But if he is choosing this lot,
Okay.
like can we assume that he is choosing Dell over?
But that is not what he's saying before, right? He's inconsistent with his own statements. So that's why it's not a rational statement. We can,
Then we have to modify that.
yeah, that's the idea. Okay. So utility theory given by Neumann and Morgenstern has one more axiom, which is substitutability. Can substitute an outcome in a lottery with an indifferent one. So I have already a lottery fixed with 30%, 70%, and I can substitute any outcome that I'm indifferent with a particular outcome, and I should get the same preference. That is substitute. And similarly, you can come up with similar inconsistencies that agents could report, sometimes. In fact, there was a study conducted and people are not rational most of the time. They come up with these numbers which are not consistent. The other thing is decomposability. This is a more of a the fact that we want to have a nice number, the ways in which we are trying to derive. So the idea is we should have same preferences for a lottery which looks like this and a lottery which looks like this. Now, what are these two lotteries? What I'm doing is let's say I have a biased coin. The coin comes up with head is with probability 0.76 and tails with probability 0.2. So every time there is heads, I pick outcome 1, and every time there is tails, I pick outcome 2. And I have a preference for this particular lottery. Now there is another lottery I conduct. This is one lottery. Let's put it aside. There is another lottery. Now I have a different coin which is biased 0.62 heads. Okay. So every time there is heads, I choose outcome 1. But every time there is tails, so there is a coin which is biased with 0.6. Every time there is heads, I choose outcome 1. But every time there is tails, I flip another coin. Right? And now the bias of this coin is 0.42. Now every time there is heads, I pick outcome 1. And every time there is tails, I pick outcome 2. Right? So now this is a kind of a lottery that I can define, right? Why not? right? So which has two parameters. Now the idea is in this lottery, what is the probability of getting outcome 1?
0.6 plus 2.4. 0.4 0.4. So it will become again 0.6 plus 1. No, 0.6.
What would be the outcome? What would be the
0.6.
probability of heads in this particular outcome?
The heads outcome 1 is 0.6.
Sorry, not heads. So what is the probability of getting outcome 1?
Yeah, 0.6 plus the remaining probability is 0.4. But if I flip again, then that's 0.4. So multiply 0.4 to 0.4, so 0.16 plus 0.6, 0.76.
So it's 0.7. Can everybody verify it's 0.76? So every time you get heads with probability 0.6 this, and then if you get tails with and then you again get heads, that you will get in with probability 0.6. Right? So if you add this, you will get 0.6. So the idea is we are just asking about the agent the same lottery, but we have worded it differently. Now the agent should be smart enough to figure this out and tell me the same utility for both of these lotteries. Right? Otherwise, he's not again rational evaluation.
Rational intelligence.
So here, for all of this, we'll just assume he is rational. Intelligence is for something else. We'll come to that later. I hope this is clear. So this axiom is called decomposability. For any simplification, so the idea is if I have multiple lotteries which are looking complex, but they mean the same, then the outcome should be the same. Then there is this axiom of monotonicity. If the agent prefers the outcome O1 over O2, then the agent must prefer all the lotteries that assigns more probability on O1, right? So that's the idea of monotonicity. If I like something better, then I like more of it. Then there is this notion of continuity, which will, this is what I was referring to when I say that there exists a combination of these lotteries which I'll prefer O3 at, right? So O3, I preferred O3 over 50% of O1 and 50% of O2. And then, but I did not prefer it as much as 75% of O1 but there should exist some number of O1 and O2, which will tell me with some probability that will reflect the exact value of O3. Now, for the existence of that, we need this property that is continuity. Okay. So if I prefer O1 over O2 and O2 over O3, then there exists a probability P with which I can represent the lottery of O1 and O3, and that will exactly determine my preference for O2, because I like O2 somewhere in between O1 and O2. So if I combine these two with some probability, there must exist some probability which will give me the utility. Now this should also be true. So these are the 6 axioms of von Neumann and Ormsted. If these 6 axioms hold, then you have got some utility. So that brings us to this theorem. So given a set of outcomes O and a preference relation on O that satisfies all the 6 axioms of completeness, transitivity, substitutability, decomposability, monotonicity, and continuity, then there exists a utility function U. I'm sorry, but it should be O instead of this. That is defined over the that maps the utility values to a value between 0 to 1. Here I'm considering utilities are normalized. So any number I can normalize them and get it to 0. For me, it represents all possible utilities. And that utility function will satisfy the following 2 properties. What are the 2 properties? The utility of O1, the number that I give for O1 will be more than O2, at least as much as O2, if I prefer O1 at least as much as O2, for every possible O1 and O2. That is what the other thing is, if the utility for a lottery, wherein the lottery is defined by these values, I give you O1 with probability P1, O2 with P2, and OM. Let's say there are M possible outcomes, OM with PM. Then the overall utility that the agent derives is given by this sum, the summation of Pj to O. So is this clear? The second point. This is quite important. We'll be using it in the later lectures where we define mixed strategies, etc. So, and to be able to define mixed strategies, this particular theorem is used. Neumann models. So, in fact, there is a very recent paper in ICML 2022. A lot of you probably don't know what ICML is. ICML is a renowned conference in machine learning. It's a very it's an A-star conference, and a lot of nice papers have come out of this venue. So what people have done is that here the utility theory is quite classic. It's been given long back, and it is just for decisions that are static. So let's say I ask, if I say there is a sequential decision making, let's say O1 happens first and then O2 happens and then O3 happens. Do you prefer O1 happening first, then O2, then O3, or do you prefer O2 happening first? So if there is a sequential nature in the way in which outcomes are happening, or there is a sequential decision making in a reinforcement learning setup or things like that, then how will we modify utility theory to come up with corresponding utility values in a sequential setup? So they have sort of extended this classic theorem to these newer domains, which are more relevant nowadays, because now people are studying sequential things that Marco discussed. So this, you should refer to this paper and see how they have. So in fact, this utility theory is being researched even now, and it's all the more relevant in today's world, right? So that's what I wanted to show. So now, because of the way the utilities are defined, this is a proposition that we have, that if I have given you certain utilities over the possible outcomes UX, and I transform these utilities and I have an affine transformation on top of it, where I multiply it with some constant A, and A is strictly positive, and I add a constant B, and B could be it. Now, this particular U dash X is also going to satisfy those two conditions. That if there is an outcome that I prefer, if U1, the idea is I had a previous utility and I preferred U1 O1 over U, there is an agent 1, over U2 O2. Now, under the transformed utility, wherein I have transformed U1 to U dash. Now, here also I strictly prefer. I suppose this is easy to see why, because I have just an affine transformation. It's a good exercise to go and prove this particular proposition. Right? I did not put it in the problem sets, but do try to see why. That if I have certain utilities and I have a preference over that, now if I modify the utilities using affine transformation, my preferences still remain the same. And also, if lotteries, the utilities that I have, the lotteries will also shift by an affine. So the preference over lotteries also remains the same. This is only true for affine transformation, which is characterized by these two constants and A being positive. Now, this means there are multiple games which can be transformed like this, and they all are equal, right? They are all equivalent. That's the idea. So we have these games called zero-sum games, the example of which we had seen in the last class, the matching coins or the matching pennies game. Right? So wherein, so this is how the game is represented. Each of these agents are, agent 1 and 2 are flipping coins, and agent 1 likes if both the coins have the same outcome. So whenever both have heads, agent has a utility of 1, and then whenever both have says agent 1 has a utility of 1. Whereas the other agent wants it to mismatch. So whenever there is a mismatch between the outcomes, the other agent has a utility of 1. Otherwise, it has a utility of minus. Here. We have already seen it in the last class. Now this is a zero-sum game. Why? Why?
So utility of both of them is 0.
Yeah. So the sum of the utilities for each outcome is 0. And that's why this is a zero-sum. So it's a game of strict competition. Every time I have a positive utility, the other agent has a equal negative. So it's a strict competition. It's a zero-sum game. And these games are often very easy to handle in terms of calculating what is the best outcome of the game. These games are solved, completely solved. So you can find in polynomial time, you can find what the best outcome for such games are. So it is good to study these games. And if I give you a different game, now is this a zero-sum game? It's a constant sum game. But is it equivalent to matching coins? What did we just see in the previous slide?
It's not matching coins, right? Because the zero sum is it's not.
Right, it's not matching coins. But in the previous slide, I told you about something called affine transformation. Can you come up with an affine transformation for agent 1 and then say, show that it is equivalent to matching?
Yes,
Okay, from this to that or that to that. The idea is you have to come up with a constant A and a constant B, right? What would be A and what would be B in this case for agent 1?
B certainly is closer.
Okay, if B is 0, then E is
1 by
3. Or if A is 1, then B could be 2. You could come up with multiple constants, which will get you 1 from 3, right?
But the minus 1.
Okay, then that won't work. Sorry, my bad. So you'll have, okay, A is 1 by 3 and B is 0. Good catch. Okay, so there is an affine transformation that transforms this particular matrix to this. So any so this is a constant sum game because the sum of utilities over here is 2. Right?
Some will minus 2.
Some will be minus 2 also, but the number, like the absolute number, we could say is somewhat same. So the constant sum game can always be converted to the matching coin. Now that is because of the affine transformation, the proposition that we had before. Now look at this game and tell me, is this a zero-sum game? Or is this equivalent to a zero-sum game? Are you sure? You people online, what about you? Do you think this is a zero-sum game or equivalent to a zero-sum game?
No.
The sum also doesn't look constant, right? So apply this particular transformation for player 1.
From the other one.
No. So okay. I think I lost it. So these are the utilities for player 1.
Yeah.
And I'm asking, these are the utilities given to you. Now I want you to apply this transformation where x is this. You substitute x for this and apply this. So what will it be? What will be
5,
this?
0, then 1, 5, then 0,
Will
then
this be
1.
5?
27 minus 13, then 5 to 5.
Add it. Numbers, we should-
0.
What about this?
Okay, so we can apply find transformation just to one player.
So previous case, what is it?
Okay.
So if you apply this particular affine transformation, you are actually ending up with a zero sum game.
Yes.
So this game, which is not even a constant sum, okay, still equivalent to a zero sum. And now whatever tools you have to solve a zero sum game, you can use for this. But on the face of it, you might not apply because you'll feel this is not a zero sum. So you have to be careful about this. Now I have a problem set on this. There is a formula in which to figure out if a particular game is zero sum game or not, just by looking at these, just by plotting these numbers. So the idea is, if you plot it and they all lie on a particular negative slope, if you plot these numbers, they lie in a particular line or in a negative slope, and then you know that you can convert these to a zero sum game somehow. Right?
They are collinears.
So, yeah, in this negative, yeah.
They are collinear and having negative slope.
So this particular information is there in the Griffin's, the reference one. You should go and check it. Okay.
Ma'am, I have a question here.
Sure.
So, if we need to convert into a zero-sum game, so do we have any algorithm to get it? Means, if it is a kind of a combination of number where we want to convert this into a zero-sum game, so how
So
to
first
do
of all, you have to check if it is even possible to convert it into a zero sum game or not.
so
So
how?
for that possibility, what I'm trying to say is this: if you plot all these numbers on a particular graph, they'll be in a line with a negative slope. They'll be all on a same line. In that case, you can actually convert a game like this to a zero sum. I'll just give you some random. So, for example, the matrix that we had for Prisoner's Dilemma, could you convert that somehow into zero sum game?
So ideally, we'll have to plot the numbers, and based on that, we'll have to see.
Yeah, you'll have to do this. So this game you cannot really convert it into a zero sum game because this is not a zero sum game, neither equivalent to it. There exists no affine transformation that converts this into a zero sum game, but there exists one here because this follows a certain pattern, and then you figure out what is it that gives you the values that you need.
But they are not running the same way. Those exist.
That's the idea for that. Okay. So this brings us to the first notion or first assumption in game theory, that is agents are rational. The first thing that we want to say is that because agents are rational, they want to maximize their utility. But does this really mean anything? Can they try to minimize their utility? They can, but it just means that the utilities that you have extracted are opposite, right? You have to reverse the utility there. So trying to maximize their utilities is just a convention that we are following. So in the world, we have this convention that there is a direction which is north, there is a direction which is east, west, south. Those are just names, don't really mean anything. You could absolutely rename it and it would still mean this, right? That's a convention that the entire world has stuck to. Okay, that's north, this is east, this is west, and this is south. Similarly, here we are also sticking to one convention, that is we want the agents to maximize their utilities. Because we want agents to maximize their utilities, there is a certain way in which we extract utilities out of preferences that we have different. So that is one assumption about rationality. The other assumption is that they must report consistent preferences. Now, how do we define consistent? All the 6 axioms that we had, right, in the utility theory. If the utilities that they report are consistent, satisfy all the 6 axioms, and they are consistent, and we can assign some cardinal utilities, and therefore the agents are rational. So I hope this is clear. So the idea that we are thinking that, yes, some question? The fact that we want them to just maximize their utilities means that we have extracted the utilities in a certain way. But the main idea is that they have consistent behavior. That's where rationality comes.
Maybe they are consistent, but more like fun like or rational or not.
Maybe they are consistent, but not in game theoretic sense. No, if they do not satisfy the 6 axioms, then for us they are not rational.
They have consistent behavior, but not in the cardinality form.
No, we have defined consistency in a certain way, right? You cannot change the definition of consistency. I want you to be consistent in this way and satisfy the 6 axioms. Only then I'll say you're rational. Otherwise, you're not rational. I can't be. Otherwise, you can come up with a utility theory wherein you are able to extract cardinal utilities about that consistency and then design your game. That's absolutely fine. But the games and the kind of analysis that we are going to have, this is what is required. Certainly, this is not enough, I guess. There is so I can't keep so practically speaking, I can't go around asking these lottery, right? Do you prefer this over that? And for that matter, if you tell me a lottery, I can't even assign a number to it. So I'll prefer 50% of this, 30% of this over this. I don't really know, right? It's not really a very practical way. Maybe you guys can come up with something more practical so that game theory becomes more applicable. That's a one big issue actually when it comes to applying algorithms of game theory. Okay, that's this assumption of rationality. The other assumption, so are the agents really selfish here when they are trying to maximize the utility?
But also dependent.
What does that mean?
Like decisions of other also changes their preferences.
Yes, that is okay. That has nothing to do with being selfish. So what I'm saying is they're maximizing their utilities. Agents, that is why we say agents are selfish, because they only want to maximize their utilities. But let's say in a world there is an altruistic agent who is wanting the welfare of everybody else. So the utilities that the agent will define itself will change, right? So if I like you getting more utility, then I'll assign that more number. So I'm still selfish at wanting the fact that you should get more. So agents are selfish, but that really doesn't mean selfish in our context. It's just the way you're defining it. Okay. And the next thing that we have is the assumption that agents are intelligent. Now, agents want to maximize their utilities, but can they really maximize their utilities? Do they know how to do the math to maximize their utility? So for that, we assume that agents are intelligent. And like you mentioned, the utility is not just dependent on his own action, but it is also dependent on the action of every other. So now, since I am intelligent, and the assumption is that all the agents are intelligent, I also know you are intelligent. So what would you do if this is the situation? Because you are intelligent. And I'll factor that in my calculation and then try to see what is the best thing that I should do. Right? For me to maximize my utility, there is a constraint. And what is the constraint? The constraint is that you'll also maximize your utility. That's how you will play. So if you maximize your utility, what is the possible options that I am left with? And based on that, I'll try to maximize it. Now, you also know that I am intelligent. So when you are maximizing, you'll also factor in mine. I'll also factor in yours. So this is what is leading to this notion of common knowledge. So intelligence is intelligence is the point that the agents are smart enough to maximize their utility, and they're smart enough to also know that other agents are intelligent and they are maximizing. Okay. Yes. So an intelligent agent would take into account all the information available. The expected, not in the average sense, the expectations that he has about the other agents, the best behavior that they have, and then he'll come up with his own optimal strategy or the best response strategy. So now this agent being intelligent also implies common knowledge. So so everybody knows. So we have upfront told the entire world that all the agents, when we are modeling, all the agents are rational and intelligent. This means that I am not the only one who is intelligent. Everybody else is. I know it. So if I know I am intelligent, I also know that you are intelligent. I know that you are intelligent, and I also know the fact that you know that I am intelligent. So when you know that I am intelligent, you'll act certainly, and I know all of this. So what is the way? And like that, you can keep going on. I know you know that I know you are intelligent, and so on. Right. So this is common knowledge. So the fact that you act based on the fact that you know the other also knows what you know, and this is also a known fact, and so on. So this particular things arises certain nice puzzles that we will look at in the following. So I hope the people online are following. They know what intelligence is, rationality is, and common knowledge is. So let's see if you are able to figure this puzzle out. So this is based on common knowledge. So in an island, I think most of you have already seen it online before, but sure, for those of you who have not. So in an island with no mirror, there are and no water bodies and no whatever. So I basically don't know what my own eye color is. So with no mirror, there are K blue-eyed people and the rest are black-eyed. Now the rule is all the blue-eyed people must leave the island or they'll be killed. Whatever. The Hunger Games. So in an island, there are K blue-eyed people and the rest are black-eyed. And the rule is that all the blue-eyed people must leave the island. So everybody is able to see everybody else's color of the eye, but they are not able to see their own. So now what happens is, in this situation, can people really know if they are blue-eyed or black-eyed? Maybe, maybe not. But what is happening is there is some information that is being given to them. So there is an outsider who is making some announcement. What did he announce? He announced that there is at least one blue-eyed person in this island. That's what he announced. Now there is in an island, there are K blue-eyed people and one black-eyed people. The idea is for the blue-eyed people to leave the island. But now to help them, there is one announcement that is made. There is at least one person who is a blue-eyed person. Now what will happen? Will the blue-eyed people leave the island? Will they stay? Will one of them leave? Will none of them leave? What will happen?
They don't talk to each other.
They can talk to each other.
White person get there. The black-eyed person get there.
If K is one, there's only one blue-eyed person. What will happen? Sorry. So if K is equal to 1, I put green and green. Sorry. Okay. So if K is equal to, if I am a blue-eyed person and I only see black, let me just change this to black. Not if you attend a lot of lectures and have a lot of people give a lot of different colors, this is what will happen. So I see only black eyes, right? I am the only blue-eyed person in the island. I only see black eyes everywhere, and I know the announcement that I'm intelligent. And I have the announcement says that there is at least one blue-eyed person, and I only see black eye. That means I must be that one blue-eyed person, right? I'm smart enough to figure that out. So what I'll do, I'll figure that out and I'll leave. That's what I do. No, everybody is seeing everybody. Let's assume that it's a small island, Andaman. K is equal to 2, what will happen? Sorry.
The other person
See, sure. So they, yeah.
And then
So in the K is equal to 2, the case, yes. So he'll have to agree this. Yes, that's exactly the point. So the first day, what I see is I see one more blue-eyed person. Then I am happy. Oh, I think everybody else is black. but there is one more person who is blue-eyed, so he must leave, right? Because there is at least one blue-eyed. But the next day I come and see that fellow has not left. What does that mean? That means there is somebody else, he's also seeing me and seeing that I am blue-eyed. I'm also not leaving, he's also not leaving. So next day, both of us will figure out, oh, both of us are blue-eyed and blue-eyed and got this argument?
I don't understand one thing.
But
Twice
we
here,
are not going to have to say that there is at least two people.
No. At least one is enough, right? Why do we? Because this is where the you know that I know factor comes in. So the fact that only at least one blue-eyed person. The first day I see you, you're not. I know you should leave because you have blue eyes, but you're not leaving. That means what? What will I understand? I'll understand that there must be one. You also are seeing me, and you're thinking the same. That's why you have not. That's why now both of us have come to a conclusion that both of us are blue. Just with that enough. The announcement did change. Right. So similarly, like he said, the inductive argument will keep on going. Every day we'll come together and figure out, oh, you've also not left, then I must be the culprit. So we'll all leave. That's how the entire island will be gotten rid of the blue-eyed. So this is the idea behind common knowledge. So there is one assignment question on that. So I hope you guys figure it out. So a brief recap. So what we saw today were certain key notions in game theory. We saw what is utility theory, what are the assumptions required to come up with these cardinal utilities for every possible preferences, right? And that in turn tells us who is an agent that is rational. And rational agent is one who is able to come up with these consistent preferences and is also wanting to maximize the utility. So the utilities that we extract are such that he prefers the outcome in a certain way, right? And then we have this idea of intelligence. That means agents are intelligent enough to maximize their utilities, and they also know that the others are intelligent, and so on. So that comes up with this idea of common knowledge, where we all know. So this entire information is known to the public, and all are smart. So how are they really going to process this information before coming up with an outcome? Okay, so that's so that ends the entire story about the notions and the assumptions that we have in game theory. Now, given that all these assumptions are in place, we are going to do a brief recap about the notations that we introduced in the previous class, and we'll see what is the best practice. So this is a good time to ask any questions or any doubts that you have.
The blue-eyed. That blue-eyed meaning. Why don't you say each other you are blue-eyed? I see a blue-eyed person and you're blue-eyed.
But okay, but what if you're just wanting me out of the island? Because there are not enough resources for us to share. You're wanting me out of the island, I'll just tell you you're blue-eyed and I mean, I could be fooling you also, trying to fool you also, right? To leave the island. Yes, sure. And if a lot of people are there, then more people to divide the risk. Yeah, I should rewrite the example more appropriately. Just check if there is something. People are following. Okay, so last class we saw this thing called strategic form games. We have some n set of players, and the strategies for each of these players is represented by these sets called S1, S1 set. And we have defined certain payoffs or utilities to each of these players. and that is defined over the Cartesian product or the set of strategy profiles to this real variable. We saw today how to come up with these utilities. We assume that these exist, these are consistent, all of that. And this is the strategic form game or the normal form. Right? So for prisoner's dilemma, we have two agents, A and B, and these are the different possible outcomes or strategy profiles. And there is this common notation for utility that we'll be using throughout the lecture. So please ensure that you understand what this notation really means. So UI, so every utility is corresponding to the entire set of strategy profile that I have. So this is one particular strategy profile that I could select out of the entire scale. And that represents the utility that agent I derives. And now this is a new notion, new way of representing my utility. The same utility can be represented like this, where SI is my strategy and S minus I represents everybody else's strategy except. So this is one way of representing the utility or the strategy profile. So either you write S1 up to Sn, or so the same strategy profile is small s, what I'm writing over there is small s, and can also be represented as Si, comma S1. I'm just trying to, because here we are going to analyze a lot about how utility changes with my change, with the change of my strategy, given everybody else is playing something fixed, right? So I want to fix everybody else's strategy to S minus I, and I change my strategy and I see how my utilities change. So which is why I want some notation like this to make things easier for me. So S minus I is all the strategies except the I. So in the prisoner's dilemma game, what would be, so here there are only two agents. So for any agent, if that particular agent is confessing, and when I say S minus I, that means the other agent. Since there are only two agents, it's not me, so it's the other agent. If the other agent is not confessing, and what would be my utility? Don't remember the methods.
Confessing and not confessing.
Minus minus one, right? If I'm confessing, I'm so it's okay. It's a matter of remembering the utility values. So now let's try to understand what is a best response strategy in a prisoner's dilemma. So when the other person confesses, what should I do? So if I look at this particular matrix, and what I have fixed here is that the other confesses. When I say the other, I mean S minus I. Okay? Now S minus I confesses, so I have put C over. I have fixed the strategy of the other agent. Now the other agent could change depending on who I am. So we'll have to argue for both. So for the row player or for player A, if the other agent confesses, what should I do? If I confess, so how do you read this matrix? So now we are trying to focus on the row player, right? And I have fixed the other agent strategy, which is the column player strategy, and the column player strategy is to confess. So now I have to only focus on this part of the matrix. The other player is confessing. So if I confess, I get a utility of -5. And if I don't confess, I get a utility of -5. Now I'm trying to maximize my utility. So if the other player confesses, what should I do?
Confess.
Because utility of confessing is more than utility. Yes, question. Okay. Now similarly, so this represents my row player's utilities. This is because I have fixed the column player strategy. Now, if I have to argue the same about the column player, that means I now is column player. I is equal to A. So minus I will be A. So now I have fixed the strategy of the other agent. Now the other agent is confessed. Right? So what should I do? So if I don't confess, now you'll have to look at the second values, right? If I don't confess, I get a utility of -10, and if I confess, I get a utility of -5. I should still, because I'm maximizing my utilities. So no matter who I is, either the row player or the column player, if the other person is confessing, I should always confess. That's my strategy. Now let's argue the same for the other strategy. So when the other player does not confess, what should I do? Okay. So when S minus, I'm just trying to help you with the notation, see how the notations are built so that it becomes easier for you to analyze it when I'm using these notations very frequently. Okay. So when S minus I is NC, so S minus I, and if I am the row player, so for the row player again, now we have to fix this particular part of the matrix. The other player is the column player, is not confessed. So for me, confessing is -1, but not confessing is -2. So I should still confess. And now for the column player, the other player is the row player, so I'll fix this part of the matrix. And the column player will compare between these two values. So I should still. So if the other agent is confessing, no matter who I am, I will confess. If the other agent is not confessing, no matter who I am, I should confess. So what should both the players do? So the C and C is the predicted outcome of the game. So this is what is an outcome of the game. The agents are smart, rational, etc., common knowledge, all of that. This is what people will do. They will, and they are trying to maximize their utility. They will try to figure this matrix out, and they'll see if confessing is the best strategy for me to do this way. Now, is it the best outcome? Not really, right? So there is, because if you see the matrix, both of them can actually go away with lesser punishment or more utility than what they have got. So if agents are intelligent, they still can't do the best things for them. That's a world we are. Okay. Any questions? Any difficulty in understanding the notations? Please, this is a good time to ask questions or doubts. So if I give you a game like this, and here, if you see, I don't have two utilities. I just have one. I only give you the utilities of the row player. So this is the column player, and he has three actions: small a, small b, small c. And I have a row player one who has three actions: capital A, capital B, capital C. Can you tell me what should the row player do? Even if I don't tell you what the column player is, I don't really know what the other person is, what the other person's utilities are. Ideally, I do know, but here I have not given you that. But even without knowing it, can you tell me what should be the best thing for the first agent? One of you who has not answered, could go ahead and answer this. So somebody from online could try.
Should we interpret what this utility says, right? That's what we need to.
So these are the utilities for the row player. What I have given you in this matrix is the value that player one is getting when the actions that are written over here are played. Okay. So what should really the player one do? Should he play certain action, or should he, or can't you can't say. You don't really know what player one should.
I think informations are not sufficient.
Okay. Why? Okay. Information is not sufficient. What about you guys? Do you also think the same? So the thing is, if you look in the other player, okay, if I play A and the other player plays any of the three strategies, how do we? So the idea is that there is a particular strategy which is giving me highest utility no matter what the other agent is playing. If the other agent, let's say if S minus I is equal to A. So I is equal to 1. I is equal to 1. So I is 1 and S minus I, that means the strategy that the second agent is choosing is A. Then what should be my strategy?
In capital A,
So if the other agent is playing small a, my strategy should be, since I am trying to maximize my utility, I'll fix this particular column. I should always play capital A, right? Because that is giving me the most utility out of the 3 strategies that I have, given that the other player is playing A. Similarly, if the other player is playing B, I could choose either A or B. If the other player is playing C, I could choose either A or B. But if I don't know what the other player is going to play, then it is good for me to stick with capital A because it's always giving me the highest utility, no matter what the other player is. So utility of agent 1, when agent 1 is playing capital A, and S minus I is anything, is greater than utility for Si, comma S minus I, here. So for I is equal to 1, and for all possible S minus I, and for all possible Si, this is T. You should be able to read these notations because from the next lecture onwards, I'll load you all with all these notations. Okay? If not for all, sorry, we can't selectively erase. So if I is equal to 1, for every strategy that the other agent is playing, for all possible S minus I, and for every strategy that I can play, playing A is maximizing my utility, is always giving me higher utility. That's how you. I hope the one who asked the question, it is clear now that A is the dominant, A is the strategy that the player 1 should play. Or is it still not clear?
No, ma'am, still not clear. I'm not able to relate that.
So what is your doubt exactly? Why do you?
So the doubt is if player 2 chooses a strategy of A.
No. Okay. Player 2 is playing A, so we are in the first column.
Right. So if player A chooses the strategy of small a, right? No, sorry, capital A, right? That's the player 1.
Yes.
Player 1. So first of all, the player 1 play the game, right? Then the second player will come into the picture to choose their highest priority.
No. Both of them. So in all these games, both of the players are simultaneously choosing the strategies. Here we are just trying to analyze. So when actually player 1 is going to choose, he is an intelligent player, so he is going to analyze what if the other player chooses A, what should I do? What if, so nobody is really choosing. Here player 1 is trying to analyze what to choose. So if the other player chooses small a, my utility is maximized when I choose capital. Is that correct or not?
Yeah, correct.
Similarly, if the other player is choosing B, then my utility is still maximized when I choose capital.
Okay.
So no matter what the other player plays, my utility is maximized when I choose capital. That's what I have written mathematically over here. No matter what the other player chooses, if I play A, then I am getting the maximum.
So then Si equals to capital A and then S minus I. What does it mean? Why S minus I?
S minus I represents the strategies of the other agent. What could S minus A be? It could be small a, it could be small b, it could be small c, right? It could be all the 3. So no matter what it is, it could. So S minus I, I'm just using it as a placeholder for any of these 3 other strategies.
Okay. So I is for player 1 and minus I is for player 2. That's what, right?
Yes, exactly. If
Okay.
I is equal to 2, then minus I will be for player 1. So
Okay.
I means I and minus I. Minus I is everybody except.
Okay.
Okay.
Got it, man. Thanks.
Great. So let's go on. So there is one more game that we had seen in the front in before that chilling in the room and going to class wala game. That's also called a coordination game. It's also called the Battle of Sexes game because so those of you don't remember, what we have is two students and they like to do things together. That's the idea. And each of them can't decide to do what they have to make one of the two decisions. They either want to attend the class or relax in the room. So C for class and R for room. And I slightly changed the utilities from before. So when both of them are in the class, each of them get these particular utilities. And one is in the class, the other is in the room. These are the utilities, and both of them are in the room. These are the utilities. Now, can you tell me what should each of them do? Is there any dominance? Is there any strategy that one must do? Can you try to figure it out for each of the? So for when I is equal to 1, and S minus I, that is second agent strategies could be either C or R. So if I go to class, then the other agent is going to class. And if I stay back in room, then the other agent is going to class. How are they related? So if I go to the class, so now what I've done is I have fixed S minus I. I have fixed S minus I to C. Now you focus on this part of the matrix. If the other agent is actually going to class, for me it is good. It's the best strategy to go to class because 2 is greater than display. So that is something that we have fixed. Now, if let's say the other agent is in the room, so I put R over here and U1 C S minus I is equal to R. Yes. So now if I now we have fixed this part of the matrix, but here interestingly staying in the class as going to the class as before is not the best strategy because we like to do things together. If the other person is in the room, I also want. So now the idea is that now my best strategy is not well defined anymore. It now depends on what the other player is doing. So that's why it's called the Battle of the Sexes game. When there are two people in a couple and they have different interests, but then they want to do things together. There's no really solution. No solution to it. It's not easy way out. Okay, so what should each player do is not clear.
So they are actually for it be better if they actually just one day they actually
Sure. It's one of the future, but we'll come to that. So there is what I'm trying to say is that there is no easy way of figuring out what you. So in the previous prisoner's dilemma case, no matter what the other person did, I had a dominant strategy, a strategy that I should do irrespective of what the other is doing, and that was same for both of the agents. But in this case, I do not have a strategy which is dominant, right? No matter what the other is doing, I cannot. It depends on what the other is, what I should do. So the strategies that we saw today are called dominant strategies. Confessing dominated not confessing for every strategy that the other player plays. Or it could be written in this way. SI star I'm denoting as the dominant strategy. It is the strategy that is giving ith agent more utility compared to every other strategy, and for every other strategy that the other agent does. So this is the definition of a dominant strategy. So confessing was a dominant strategy, and not confessing is a dominated strategy. Because there is a strategy that is strictly dominating that gives me strictly better utility, no matter what the other person is doing. So not confessing was a dominated strategy. And the coordination game really had no dominant strategy or dominated strategy. So let's look at one more game from the problem set and try to figure out what the dominant strategies are there. So that's a game. Okay. Before we move on, is there any doubt regarding what is a dominant and what is a dominated strategy? People online also could ask some. Yes. Or? Oh, the previous game. Okay. For which agent? Both rest. Okay. So for agent 1, let's say. So, but if agent 2 is playing rest, what will agent 1 do?
Oh,
They'll
keeping
go.
up.
Till we are. But if this particular. So your doubt is why this is not a dominant strategy and both are playing hard. So if the other if agent 2 is playing R, I'll play R. If agent 1 is playing R, I should also play R. But the definition of draw, so this is essentially a Nash equilibrium of sorts here, because when the other agent strategy is fixed, my strategy is hard. But dominant strategy is telling me no matter what the other agent is playing, I should play R. So if the other agent plays C, I cannot play R, right? Right? So that is why it is not dominant. It is not dominant because dominant strategy is a strategy which gives me better utility no matter what the other agent is. Zero comma 3. Yeah, 3 is greater than 1 and 2 is greater than 0.5. So, sorry, that's not how you. I'm 3 is greater than, so you have to only compare the column player strategy. So 3 is greater than 2 and 1 is greater than 0.5. So C is a dominant strategy for the second. For player 2. Player 1, you did not change the utility, so now still player 1 won't have any dominant strategies. So there is a dominant, one of them could have dominant. So that's the distinction that you should remember. A dominant strategy is a strategy which is giving me higher utility no matter what the other is. You fix the strategy, the story is. Similarly, if you argue for this, you'll get the same sort of thing. So if the other player is playing C, I should play C if I'm playing C.
The second row at one point and the first line is actually 10.
Okay, I have a problem set here. The first problem over here is again is regarding the affine transformations that we saw. I gave you 2 matrices, and I want you to figure out which of these 2 matrices is equivalent to a zero sum, and which cannot. Problem 2 is a problem on common knowledge. You should tell me the answer because I still have to calculate. And problem 1.3 is regarding dominant strategies. So this is a Newcomb's problem. I hope it's. Oh, people online are able to see. I've shared the screen.
We are able to see, ma'am, but if you could zoom in, yeah, thanks.
So this is a nice model which has been liked by a lot of people. It's called Newcomb's problem and the problem of free will. Now they are trying to model that as a game, and this is the game. And we are going to try to see if there is a dominant strategy in this. So now what is happening is there are two black boxes. You are not able to see what the contents of these black boxes are. In one of these boxes, there is 1,000 rupees. And in the other box, there is either 10 lakhs or nothing based on a particular prediction, based on something, based on God's prediction. Okay. Now we'll shortly see what God's prediction is. But then there are two choices that this agent has. Right. Now the agent can either take both the boxes, 1,000 and possible 10 lakhs, that is strategy A12, or could only take the second box. Now what God has done, let's see what God has done before. Now before that particular person was born, long before, God has very super predictive. It's a deterministic world, you know. He has already predicted everything that you're going to do. Now he has also predicted that what you will do. Will you take both the boxes or will you take one? Now with that knowledge, he has put some money. So if God predicted that you will only take box 2, you're not greedy, you'll only take one box, which is box 2, then he has put 10 lakhs in that. He has rewarded you for not being greedy. But now if he had predicted that you will take both the boxes, then he has, or you will flip a coin and decide between the boxes, then he has left the second box empty. He has put nothing in the second box. Now he has already done it long before you have won. Now when you are at the time when you are making a decision, the money is either there or not there. The choice has been made by them. So now what would you choose? Should you actually take both the boxes, or remember you're maximizing your still in the rational, intelligent, all that world we are there. So what would you do? Would you maximize? Would you take both the boxes? Is there a dominant? So please take your pens out and write this game in a matrix form and see what the dominant strategies are, or if there is a dominant strategy, or is there something better that we can do? You could consider that. Let's assume only if you have pure strategy, like you are only choosing one or the other. Or okay, take random choice as an action. Okay, what would be the best random choice for you to do? Because if you do a random choice, then the God is leaving nothing for you on the side. I hope people online have followed the question. Please go ahead and write the strategic form for this game and try to figure out what the dominant strategy is. You're the good guy, yeah?
Actually, God prediction is not known to a person.
God's prediction is dependent on your choice.
Yeah.
Yes.
What's the nature of God's choice?
Anything, anytime. Except probably the fact that we have picked with probability 1 and 1.
So the choice is the boxes.
It's not.
So only one of the boxes.
Yeah, only one. So not only one. If God knows that you will pick the second is an action with probability 1. That is, you'll only pick box 2. He then has to. If for any other strategy, that is mixing these two with any probability of flipping a coin, he has put nothing. It's a debate. Even the answer will be debatable. So don't hold on to me for that. There are ways in which people analyze these questions. One is using dominant strategies, the other is expected value and things like that, but none of them will satisfy you. Expected is in the sense that you first figure out what is the dominant. I'll come to that. Tell me what's the dominant strategy. Just some water and cup. So any answers, any intuition? Huh? Taking box 2 is the best. Okay, so even if God was more than 50% accurate, 51% accurate, still I would benefit by only taking 2 boxes, right? That's correct, but is that a dominance? So when you argue, yes. So even if you assume that God is, let's say if God is accurate, then though, even if you assume that God is only accurate by small marks, by 51%. Okay, what was your argument? Can you tell me? Okay, God.
Any other thing you have seen?
Oh. Okay.
God is accurate 50-50 of the time, then there is like
Right, right. So let's say so God has already made his. This is one more school of thought which is coming from the dominant strategy. So God has already made his decision long before. Either the money is there or not there. And God, in some sense, if I take both the boxes, I am guaranteed 1,000 rupees. If God has made a prediction that I'll take both the boxes, then he has actually left nothing in the other. So it is good for me to take both of them so that I'll at least get 1,000. Or God's prediction could be correct that you will take both the boxes.
So then I have no choice.
In that case, God must have left nothing with you. Right? If God is correct and he has predicted it,
He's going to boxes and realize what
Is there any scenario where I open
in
this?
the box and he was
So, I mean, that could be the. So if you take both, maybe God was correct and he has left nothing in that, and you'll be ending up with 1,000. So that's something you would have gotten. So that's the utility that you will get. Had you taken only box 2, then you will get a strictly less utility. Right? Strictly less utility. Because if you are greedy and you wanted to take both in this situation when you are greedy and you had to take both, but if you only take 2, then you would be left with nothing. God was wrong in this case. But God has already made whatever his prediction was, and he's left. So the dominant strategy kind of people, they try to look at this scenario and say that no matter what God has done, it's always good for you to take both the boxes because you're guaranteeing yourself 1,000 rupees. So if you apply the math, but this is not correct. This is not giving you the correct because of the very reason that you're saying. Even if God had a 51% chance of predicting what you would do correctly, you will still get more utility by picking only box than picking both. That's one more way of arguing. So even if I define the dominant strategies, if you blindly apply that over here, it will only tell you to take both the boxes. It will only tell you that that is the dominant strategy. You directly write the utilities and so being greedy is like the dominant strategy in this case, but well, that's not giving you the dominant strategy is that because if God had predicted, no matter what God had predicted, right, you don't really care about no matter what his strategy is. So must be correct. No matter what his prediction was, for you to take both the boxes is going to at least guarantee you 30,000. Okay.
If you take 2, there is a chance you might get that 10 lakh, but you don't get that 10 lakh. But if you take 2, you get 10 lakh. That's how it's going to happen.
Okay, if the God's predictions are 100, in that case, you are settled with what your answer should be. It's also fine. But people have different. So if you look at different strategies about what God should do in terms of what God must. So the idea is that the money is already there or not there, irrespective of what you are going to. So here the idea is to try to define, is there really a free will or is it very deterministic? If you have faith that it is deterministic, then you would choose box 2. But if you think it is based on my own will, then you will say, oh, look, let me.
Other person other than God.
Then you would have.
What person? Because God is. Like,
because you believe in God.
God.
Okay.
Sorry. The thing is, God, I mean, you should say it has a.
Super predict. The way I have defined is sort of giving you the fact that he will.
Game maker, and that person has left you 2 boxes. Then okay.
Sure.
Can we say that no matter what I choose, suppose E1 or E2, the utility coming from the box 2 would be same. Suppose 50% of the time I get like there is money in box. So you can see that in both the options, there is 50% probability that there will be some probability that there will, but it will be same for both the options.
Good. So the idea is if you are not greedy and you always want to pick only 2, that means God has already put 1 lakh, 10 lakhs in that, right? So now if you take both of them, you'll get 10 lakhs plus 1,000. And then you are greedy. So God has probably, but if God has already predicted that you are not greedy and has done it before, long before, isn't it good that you take both of them and get the 1,000 as well? We don't know it. That's the entire point, right? We don't know in advance. But if you think that he is predicting you are not greedy and has predicted that you are not greedy and he has put in the 10 lakh, then you take the 10 lakh and also the 1,000 because you are maximizing. But then his prediction is wrong. But even if his prediction was correct, he would have put 10 lakh
One disclaimer, God can explain.
Okay, so that's it for this class. In the next class, we will see what are dominant strategies in detail, weakly dominant strategies, strongly dominant strategies, and what is a dominant strategy equilibrium. And we'll look at some games like the Brazes paradox game that we had in the problem set 1. We will try to analyze what is a dominant strategy equilibrium there in a Brazes paradox game, and also try to see why dominant strategy equilibrium is not enough to modify outcome of different games. For example, the Battle of Sexes did not have any dominant strategy for any of them. So dominant strategy equilibrium is an outcome that is a good outcome, but it's not possible in every game. So what other possible outcomes can we look for, or game theoretically good possible outcomes in a particular? So that's what we are going to see in the class after. Thank you. Thank you for attending. Any questions on online? You could also ask any questions in the notations or all of that if you have any doubt.
Something abstract.
We had the doubt about rationality. So Brazes patterns. Nobody has doubt. Stop recording this.